Hello, Internet. Welcome to the first video of the TouchDesigner audio-reactive series. In this video, we will see how to create the audio-reactive composition you see on the screen. This series is designed to explore some techniques related to audio analysis and audio-reactive tools. As the channel evolves, we will create custom components to improve our workflow. Honestly, I believe this topic is one of the areas where ideas, methods, and concepts can be most developed, so this is just the first video showcasing some possibilities. Warning: this video can be approached in two ways. The easiest is to understand the basics of using audio to manipulate parameters. The second way is to follow along and create this composition step by step. To do this, you'll need my custom component called pseudo-liquids. You can find it in the tutorial linked in the description, or get it directly from my Patreon. The composition I'm using is also linked in the description. I know some might find navigating through other videos annoying, but many new viewers appreciate having everything well structured for learning. This video focuses on audio-reactive techniques without the distraction of creating a composition from scratch, which would take much more time. Before we continue, if you're completely new to TouchDesigner, you only need to know one thing for this video: how to call operators from the menu. Press the Tab key to open the pop-up window with different types of operators marked with colors. Select the top operator section, type the name of the operator you're looking for, and it will highlight for easy selection. Click the operator's name and drag it into the network. If you want to call another type of operator, like an LFO, repeat the previous steps, but this time select the Chop tab to call an LFO. If you want to learn more about operators, you can check out the video linked in the description. Normally, I don't show the pop-up window in my tutorials, so remember what I just taught you. Chapter 1. Network. Now let's create the network as we usually do in my tutorials. Alright, let's start. First, drag the audio file you want to use into TouchDesigner. Next, connect an audio device out. This ensures we can hear the music. However, we will mute it by clicking the arrow because we don't want the loop distracting us for now. Next, go to the TouchDesigner palette, look in Tools, and find Audio Analysis. Connect the output of the audio device out to the input of audio analysis. Now insert a select and organize as follows. Duplicate this select and place it below. Then create a count, followed by another count operator, and finish with a null, which we will rename to invert. Great. Select this entire network, duplicate it, and replace one count operator with a new lag. Finally, add a null, followed by a math operator. To finish this part of the network, add a lag, and after the lag, place another null. Don't forget to rename the three nodes at the end. The first one is labeled as inverted, the second one will be translate, and the third one we will call dimmer. Perfect. Continue with the network below. The first thing we will create is a math, followed by a lag operator, and we will finish with a null. Copy and paste this sequence 4 times. Let's organize this a bit more and rename these operators as follows: snare 1, snare 2, blur 1, blur 2. Great. Above this network, I will create the following mini chain of operators. Use an operator called trail because I want to see the values coming out of the different parameters from the audio analysis. Connect this select to the first input of the trail. And following this last operator, connect and analyze. I will explain why later. Perfect. Let's copy the trail, paste it, but this time, connect the first math to the first input of the trail and repeat the same with the second. This is mainly informative. I want to show how the frequencies we will use to parameterize the animation of our composition are behaving. For now, we have almost everything. Let's go up and create a new mini network for using colors. Create a constant. Set this constant with 3 channels, which we will rename to R, G, and B. Now duplicate this constant operator 3 times and create a switch on the first constant and connect the rest of the constants to the switch. Be careful, the first connection is duplicated, so let's disconnect this. Now we have 3 constant connected and everything is set. Great. Up to this point, we have almost everything ready. We will create one last network with another operator we will use quite a bit. Don't worry if you didn't understand what we did so far. I will explain these chains of operators in more detail later on. Let's move on to the second section of the network and start by creating a beat operator. Connect a select operator to the beat operator. Select it and duplicate it twice. Feel free to arrange the network for better organization. Following the first select, connect a logic operator. After the logic operator, add a math operator and finish with a null. Rename this null at the end. For the second select, only use a null at the end of the network. For the third select, use a count operator, followed by a null. Rename these 3 null operators as follows. The first one will be named X scale. The second one will be named select switch. The third one will be named select blend. Great. We've completed all the networks we'll use to operate with the audio analysis. Let's move on to the next part. Chapter 2, Audio Analysis Tool. The audio analysis tool is a custom component that extracts useful information from audio frequencies to use as modulators in your compositions. It analyzes input audio waveforms for properties such as low, mid, and high frequencies, and can also recognize rhythm, kick, and snare from a song. Let's review this concept with a practical example. I have imported 2 audio tracks. One is a kick drum loop that sounds like this, and the other is a medium percussion track with a snare sound. Keep the first loop active. Click on the plus button to activate the tool, then activate the kick and observe how it reacts to the music. You may need to adjust the threshold until the light turns on with the kick's rhythm. If you want a more detailed view of what's happening, create a select operator. Now, let's activate other options of this tool. For example, we can activate the low frequencies that typically correspond to the kick, bass, or pads in a song. Let's see how the indicators react now. As you can see, it activates with each kick drum hit, but note that 2 important things are happening. Let me explain. When we activate the kick recognition, this tool gives us a value of 0 when it is off and 1 when it is on. This type of Boolean value is useful for certain types of parameter manipulation. In contrast, the low frequency recognition captures the entire dynamic of the frequency, meaning it recognizes the complete movement that this frequency has in volume over time. This means we can see this movement reflected in a parameter that will have different uses compared to a Boolean value, as in the case of kick recognition. Both methods are useful. Now, let's turn off these 2 and turn on our percussion loop. This loop is a mix of snare and mid-frequency percussion elements. Sometimes the tool doesn't recognize the snare well, even with threshold adjustments. For now, try to find which parts of the audio frequency work best for what you want to do. Perfect. This is all you need to know for now, and it will be useful for the rest of the tutorial. Chapter 3, Prepare Operators. Let's prepare some parameters in the operators we created earlier. Unlike my previous tutorials, I will pause to explain certain details in specific operator chains. First, rename this section to colors. This section will manage 3 different colors that will interchange somewhat randomly using the switch operator at the end of the network. Creating this section can be a bit tedious because you need to create a constant and choose the desired color, such as red or orange. You'll need to manually enter the values for each color into each constant. And every time you want to test a new value, you have to repeat the process, making it a very time-consuming task. To streamline this process, I created a component called ColorPicker, which will replace the 3 constants, saving us time. I'll place my color picker here and duplicate it twice, connecting all 3 to the switch. Now it's much easier to choose 3 colors, which I will map to the composition. Simply click on the desired color or drag the mouse while holding the click to explore different colors. For example, I'll choose red for the top, orange for the middle, and turquoise for the bottom. Perfect for now, and later we will map them to the operators we are interested in. Let's move to the next section, which I'll rename Kick. Start by selecting the first select and choose only the kick. Copy the following values into the network, and I'll explain why I chose them and their functions. Leave the second network as it is. Go to the last part of the network and use this values in the math operator. Now, let me explain how this works. Start by resetting all counters. Every time the kick activates, the counter will count once. The minimum and maximum values create a loop. When the counter reaches 8, it will reset to 0. This roughly corresponds to 2 measures in the selected music. This will later be used to manipulate the invert color of the pseudo-liquids. I created a second operator where I initially set the limits incorrectly. Instead of 0 and 3, it should be 0 and 1. The second operator will change once when the first counter completes an 8-count cycle. This means the value of the second counter will change every 8 bars or over a longer time interval. The second counter counts numbers, with a lag to smooth movements. The third counter is similar to the first but uses different values. You will understand these values and why they have been assigned this way much better once we map them to the rest of the network and start manipulating parameters with the music. Perfect. Let's proceed with the final section of this audio-reactive network. Rename this section to high. Go to the select operator and keep only the high frequencies in the list. Now, I want to explain why I've created this trail, which directly tracks these frequencies. When we hit play, you'll see that the signal's peaks become visible. This signal corresponds to the snare sound, and in this case, I'm not using the snare option in the audio analysis tool. Instead, I'm using the high frequencies to obtain complete numerical values, rather than just a Boolean. Trail is very useful because it shows us the values of the audio peaks, making it easier to understand how we will use these values later. By setting the analyze function to maximum, we can determine the highest value these peaks reach, which will be mapped to our math operators. The reason for this is that we want the values to dynamically range from 0 to the maximum peak, which can change over time. For example, if we increase the volume, the peak value will change. This flexibility is crucial for modular setups, especially when working with different music tracks or different volumes in the music track. Next, map the values from the analyze operator directly to all the math operators. This setup ensures we always get the complete dynamic range of the incoming sound. Now let's mute the sound for a while, and I will teach you why I created this trail here. It allows us to compare the values when they enter without any subsequent mathematical processing, versus when they go through, for example, a lag, which interpolates numerical values to obtain smoother movements. Why did I create 2 extra trails here? This is to demonstrate how you can use these for any of the subsequent networks below. Place the first trail at the top and select the 2 analyze operators to compare the maximum values. In this case, the maximum value will always be 1 because my math operator is set to range from 0 to 1. However, the lag operator smooths the numerical transitions, and this transition requires time, causing the values to not reach their maximum peak. In many cases, we don't want to lose this peak value because it's essential for manipulating other parameters. For example, if we change the lag values and set it to 1, our maximum peak will now range around 0.5. It is important to consider the following. For instance, if we want to map the invert value of a level operator, using the values from the first math operator will give us the full range from 0 to 1, but with rough movements. On the other hand, using the values from the lag operator results in smooth movements, but sacrifices the full range. If we want the complete invert effect, we need to add another math operator to correct these values and achieve the full range. Once again, you need to map the peak values from the analyze operator into the new math operator to accurately define our full range. Set the output values from 0 to 1 to ensure the entire range is covered. Finally, we have the values ranging from 0 to 1 based on the original audio signal, which are also smoothed by the lag without losing the full range. It's crucial to understand that this is not a strict rule. It depends on the desired outcome and how smooth you want the movements to be. This explanation should clarify why we need these operators in our network. You can always keep a similar analysis setup for future reference. Now, copy the following values for each of the math and lag operators. These values are provisional. Later, when we map them to the rest of the network, you can adjust the parameters to your liking. However, if you want to achieve the exact results from the tutorial, it's best to use these same values for now. Chapter 3, Mapping Values. Now that everything is set up, I've activated the sound so we can listen. Let's start mapping all the values. First, select all the null operators and click on the plus sign. This will make mapping much easier. Let's begin with the colors. We will map the colors to the pseudo-liquid component by selecting the Colors tab and mapping RGB as follows. Next, we'll map these colors to the first light. Open the light options. Go back to the switch and map the next parameters. Now we have the colors set as needed. Remember, this is a switch, and it needs to change from 0 to 2 to select the colors. I'll choose a new color, perhaps a green, for the second light. That looks good. Now, since we have everything parameterized, copy this network here, place it higher up to organize the network again, and make the count change from 0 to 2 to get the two values we need in the switch. Rename this to Select Colors and map it to the switch. Now we see the colors changing over time, triggered by the kick. Next, open all these operators and place the invert in the final level of the pseudo-liquid in the invert parameter. For the translate, go to the noise and remove the default animation. Set the translate parameter here to react with the kick, adding an AB's time.seconds divided by 15 command to add some animation as it reacts to the kick sound. Now let's move on to the dimmer. I'll use it on my second light, which currently doesn't have a color. Choose any color you want and map the dimmer so the light will dim according to the kick's beat. Reference this value here and you'll see the color change. If it's too intense, go to the math operator and change the value to 5. Lastly, we have 4 more values to map. Apply the snare to the period parameter of the noise. Apply the second snare to the second displace operator. And finally, apply the blur 2 and blur 3 to the second blur in the pseudo-liquid. Now, we have a composition with dynamic changes and a lot of movement. This composition is already interesting on its own. Next, we will create mappings for the network we have here. Chapter 4, Last Mapping and Tweaks. Now that we have completed the larger part of the setup, I'd like to add some details to give this more movement, especially a glitch effect and random movements that will actually be synced to the beat. However, they will appear quite random. Here's how we'll do it. Remember that we created this mini network starting with a beat operator. I won't go in depth about what a beat operator is, because I plan to create a specialized tutorial on audio reactivity where I explain more advanced concepts. But basically, the beat operator is based on the BPM or tempo of the song. I know that I'm using a song with 138 BPM, and according to that, it will provide different types of data, such as pulse, count, bars, etc. I will focus on the beat and turn off the others. Before we continue, I want to take a moment to thank you all for watching and subscribing to my channel. Reaching over 2K subscribers in just 1 month is beyond my wildest expectations. I'm excited that so many of you are enjoying my content. However, I noticed that 76.9% of viewers haven't subscribed yet. If you found my videos helpful or inspiring, please hit that subscribe button. It's a small gesture that makes a huge difference in helping me create more high-quality TouchDesigner tutorials. Let's reduce that number. Thank you. The operators I'll use are the math, which I'll set to a range of 100 to 1, and the count, which I'll set to a range from 0 to 20. Next, we'll add some operators to incorporate additional details. I'll first create an edge operator, adding interesting textures and lines. Then I'll insert a switch and connect the last level to the switch and an RGB top to ensure a black background. I will alternate the switch between the original signal without the edge and the signal with the edge, changing every 4 beats. For this, I'll use the select switch I created earlier and map it to the switch index. Now you'll see the edge activate every 4 beats. To create lines that appear glitchy, I'll use a transform operator to stretch everything so that only lines are visible. This parameter ranges from 100 to 0 and will be mapped to the transform's X scale. You'll see lines appearing periodically. If we want to play with colors, we can create a composite operator, connect the transform and the switch to mix the two, and add another switch at the end of our network. The goal is to change the blend types dynamically with the beat. Currently it's set to multiply, but remember, the count goes from 0 to 20, so I'll use the first 20 blend types in the composite. This might yield dramatic results. I don't want them always present. Thus, I'll connect the original signal without the composite to the switch and map this switch with the select switch created previously. The blend types will change every 4 bars, and each blend will be different every 4 bars. That's it. I hope you enjoyed this tutorial. Feel free to move and play around with all the parameters in this network. Please leave your comments if you have questions or succeeded with the tutorial. And remember that the project file is available on Patreon. Thank you. This was one of the most challenging yet rewarding projects I've worked on.